the any questions about the homework? How are people doing on the homework, which I gather is due Thursday? Is that correct? That is indeed correct. Any questions or comments or interesting observations or anything about homework 3?
Professor, I had a question about the p-value test that,
P-value test, yes.
yeah, there's a task that where we have to take three individual variables and have to create three linear regression models and do a p-test on each of them. So if you could just explain how we should do the p-value test or the p-test test, that would be great.
Okay, so what am I hoping to have happen on this particular part of the assignment? Again, when we were talking about statistical significance, I talked about permutation tests. Okay, in a permutation test, you basically took the you had your original. Let's see if I can get this going here. In a permutation test, you basically had your label. If it was building a classifier, remember you're building a classifier or regressor, your label or your y variable, and you add your features x, okay? And your goal was to, and when you built a classifier on it, you got let's say, an accuracy rate of 79.3%, okay? Or you had a standard error of 23.4. Now, what I'm asking you to do is to now permute the values of the labels and try to repeat this again. Now, when you train a classifier, the x variables that you're using to build your classification, or in a regressor, I guess you're building a regressor, the y values are no longer associated with the features. It should be harder to the point of impossible to make a reasonable prediction about yourself, about what the answer should be. We would expect, if my classifier before was good, okay, then when I ran it on the permuted things, it would be less good. The accuracy on the permuted variables might be 50.1%, or my error might suddenly blow up to 123.6. Okay? What I wanted you to do was to, in a permutation test, you built 100, 1,000 random permutations, and you saw what was the distribution of the accuracies. And then you compared it to what was the accuracy of the real classifier, okay? And if the variable that you were training the classifier on enabled you to have a good prediction, okay, the accuracy should clearly stand out from the mix of random samples. If you had a variable, on the other hand, where the accuracy had, where that should have nothing to do with predicting the target variable, you probably won't be able to do better than what would happen when you had randomly permuted the labels. That was the idea. So my hope is you will find three variables, one of which is useless to predict the movie gross. That's kind of what I think you're asked for, right? You're trying to predict the movie gross. Am I correct?
Yeah.
Do you have a variable that is completely useless for predicting the movie gross?
I found that release year was pretty useless.
You found release year was useless, okay? So if that was so, building a model based on release year, okay, would, the hope would be that your classifier trying to predict the gross of a movie based on what year it was released, okay, would be, would show a situation like the green line. picking a good variable, like I'm going to guess the budget of the movie, okay, probably would behave over like that. Any questions?
So Professor, if we are doing 100 permutations, we are training the model 100 times, right?
Yes.
Okay, and let's say that my original model's accuracy is the second best one among those 101 models, where 100 models are trained on
So
permutate
now you're
random
telling me
data.
that in your world, it's not in the middle of the distribution. It
Yeah,
is over like here,
yeah.
meaning it is near the end of a distribution. Yeah, what about it?
And then the exact p-value should be like 2 by 101, right?
Something like that, yeah. So that
Yeah.
tells me that the chances of doing better by chance is 2%. Okay? Is that something to be proud of? Well, I would say not incredibly, I mean, first of all, it's what the variable says, so it's not making any feelings on you as a person or anything like that. But saying that you're doing better, than all but 2% of the random permutation suggests that model is not really that impressive. Do you kind of agree with that? Meaning that feature is probably not very good.
Yeah.
Okay. I guess, of course, any one model, maybe it's limited. Okay. The point here is to try to show how you can use and if you wanted to get a more accurate view of that, maybe if you ran 1,000 permutations, now you would get a better estimate of, let's say, is it 2% or is it 5% or is it, 0.05%, something like that. Okay. When you have a situation out here, it's probably not necessary to run too many more permutations because it's obvious you're winning by a big deal. When you have a situation like here, it probably doesn't matter because it's clear you got a loser. But when you're kind of at the border of where this is, maybe more permutations will give you a more accurate measure. Any questions about permutation tests?
I have one question. So you said that we fit the model 100 times. I'm not very clear with that part. Like, if we are taking the permutations and then, like, how are we taking the permutations and how are we fitting it 100 times and then
you're taking the permutations and you're applying it to the training data. Okay.
Okay.
So you take the training data, you permute it, and you fit it.
Yes.
And now you evaluate it on the real data. How good a model is it on the real data?
Yes.
And hopefully your model did much better before you permuted the training with the unpermuted training data than with the permuted training data.
Okay.
This is sort of a garbage in, garbage out idea. Okay. If I'm training it on data where the target value has been permuted, this should tell me nothing about the real world, right?
So, okay. So my target labels are being permitted, but my
I would permute the training labels, but not mess with the training data, mess with the permuting different records.
Yeah, and then if we are just permuting okay, so since we have permuted the labels, so our model fitting will also change.
Your model fitting will change, exactly right, okay?
Yeah.
And when you evaluate it against the real training set, hopefully it will do much, the score will get lower than what you had, okay?
Yeah.
How much does it get lower? Well, it depends upon how good the model was, right?
Yeah.
If the feature was very, very weak, and I encourage you to try one with a very, very weak feature, you will find that the model doesn't do so well, that the random permutations can catch up.
Okay.
If you do it with an important feature, the random one feature should be enough to to do much better than the other than the random model. Okay.
Yeah.
Any questions about that?
Can you assign like a confidence value to it, like when you do like a p-value test, or is this like can you not do that?
So
for-
what is the confidence value? Again, to a certain extent, again, there's a theory of confidence intervals, which I haven't gone into and stuff like that. But I think that the, you know, as far as level of confidence, when I see, when I see where I am in this distribution, the amount of stuff that is, you know, that is, again, big, you know, of random tests that did better than me, the fraction of them, that gives me a sense as to how likely did this happen by chance. Okay. Now, if you have a world where you do 1,000 random tests, okay, and you're clearly very far from, you know, the best random value didn't come close to what you did. If you really wanted to get an accurate question of exactly what the p-value is, well, then you'd have to do more and more random samples. But to a certain extent, at some point, it becomes ridiculous, right? You would say that the p probability of this, you know, happening by chance is less than 1 out of 100 or 1 out of 1,000.
But like from a permutation test, how do you show that? Do you just kind of eyeball it on the graph, or?
Well, you know how many, it's exactly, you know exactly how many values were more extreme than your statistic.
So like a percentile?
Like a percentile, it's exactly right. The p-value corresponds to a percentile, okay? If you were telling me that, you know, if you ran 100 random tests and 5 of them were more extreme than what I had, the odds that I'm better than random chance is something like 5 out of, you know, that this is due to random chance to get a score this high is 5 out of 100 or 1 out of 20. So knowing where the rank, what you care about really is where is the rank of the statistic on the real data relative to your random trials. Does that make sense?
It makes a little bit of sense, but I'm still trying to understand like how the percentile would help. Because for example, like if you have a 0 percentile, like it doesn't mean there's a 0% chance it will happen.
Well, 0%, no, but you would say that it is, you know, actually, we'll talk a little bit about discounting when you, as a way of dealing with 0. At some point, we'll talk about that. A way of dealing with 0 counts. But I would say that, you know, that if, you know, the chances of it happening by chance should be, if you've done 100 random trials, the chances of it being less than random chance is presumably, you know, of you know, having 100 random trials and none of them being as good as the statistic, yet this happening by chance, it should be realized as probably less than 1 out of 100 or 1 out of 101. Okay, so it's certainly not 0 that this could have happened by chance. Just like there's no chance that if you flip a coin 100 times and it comes up heads all the time, it's certainly not a 0 chance that it could have happened. But the probability of it being a random chance then reduces to, you know, 1 out of, you know, the number of times something like this could have happened over the total number of trials. Here you have 100 trials, okay? So something like 1 over 1, you know, the probability of this happening by chance should be less than 1 over n, where n is the number of trials. Is that reasonable?
I'm not sure.
Okay, it's reasonable to me. And again, I will admit, again, you're a little catchy with that. I am not a, you know, but it's sort of again, what was the p-value supposed to say? It is, what is the likelihood that what I saw was due to chance? right?
Yeah.
And if you play a game 100 times and you beat it all 100 times, what's the likelihood that in fact, you are not better than them? Well, it could be that if we played this more and more, okay, it would be different. But I take 1 over, again, you're doing these things at random. You're doing them independently. If it was chance, then by chance, somebody should be able to beat you, okay? And the odds of that basically are the number of examples that are worse than this, okay? That's how I interpret the p-values from permutation tests. Any other questions?
So Professor, I had one last question about the permutation test. You think we shouldn't really permute the test labels, right?
I think that it's better to permute the labels than the X values. So what do I think is bad? Let's think what's bad. Maybe I'll draw this again and you guys can decide this. Let's say you have 3 variables, V1, V2, and V3, and you have a label. I think that it is good to permute the label, okay? I do not think it's good to independently permute each column of the variables. Why is that? Because now the records are not analogous to records that you have seen in your data. They're kind of like Franken records, okay? Frankenstein things sewed up from different parts, okay? And, I think it's fair to say that if I had, let's say, let's say I took height and weight as data about a person, and I wanted to determine if they were male or female. That would be a perfectly rational kind of a test, right? Now, if I scramble the labels, I will know whether your classifier is better or worse at predicting height, the gender of somebody given their height and weight. What if I keep the labels the same in some sense, and instead independently permute the height and independently permute the weight? Note that, of course, the fact that I kept the labels the same is kind of meaningless. They're same for what? They don't correspond to anything like the same person before. But now I have, a person of small height is perfectly likely to be randomly assigned a huge weight. There's no reason why the distribution of these fake people should look like real people, okay? So this to me does not look like the same situation, okay? You don't have the same distribution of inputs if you permute the variables independently. If you permute the label, well, that seems, you still have your inputs kind of make sense, okay? Any questions?
Yes.
But Professor, I was actually asking if we should permute the labels in the test set. Is there any reason for
Permute the
doing
labels in the test set, well, then nobody should do very well. Now then, if you want to do an apples to apples comparison, suppose you train on the real data and you train on permutations and you permute the test set. Now, how will the real classifier do?
It shouldn't do really well if we permute the test
It should
labels.
do as badly as any random thing, right? So the real classifier no longer looks good compared to the fake classifiers.
Yeah.
Okay, so I would leave the test set intact, permute the labels, okay, and I think that actually is the a way that gives you a sort of meaningful comparison.
Okay, thank you.
Okay, any other questions about the homework?
So we're permuting the labels on the training set,
You're permuting the labels on the training set. That's right.
and I wonder, would the seed matter if we do multiple permutations?
Would the what matter?
The random seed.
The random seed. Well, so long as you don't use the same random seed every time you permute it, which would give you the exact same random permutation, it shouldn't be a problem. I mean, there is the whole question of how you generate random numbers is a subtle area, and I'm not really going to go into that. But, but I will assume that for most of your studies, the demands you're making on the random numbers are not so large that, basically, again, I think that just calling your random number, generally is generator should be fine. Okay. But you don't want it to build random permutations where the seed is the same at the beginning of each permutation you generate, because then you'll always generate exactly the same random permutation, and that will tell you nothing.
Thank you.
Okay, any other questions about that? Any other questions about anything on the homework? I see all kinds of, chat things here. Let's see. Anything else people want to talk? Okay, I just see the chat is all kinds of things were complicated. Anything else people want to talk about this? Anything else about anything on the on the homework? Going once, twice. Okay, so I look forward to seeing those on Thursday. The other thing that you guys should be doing in parallel is the the projects. Any questions? Again, getting ready a week from now, I need to have your project proposal. Any questions or about projects?
If we decide that we want to switch your topic later, can we do that?
Can you switch your topic later? You could, but it would be a lot. In some sense, it's a lost opportunity, because hopefully you will have done prep, thinking about what you should be doing. Okay, this is somehow 20% of the time that total time you have for your project, and it would be unfortunate if you didn't keep the same project. So my recommendation is that you spend this time thinking seriously about which topic you want. Do enough in the way of preliminary experiments to feel good about having the what data you have, and that you have directions to go in. And if you don't, that's probably a bad project. So yes, you could change, but it's probably a bad idea. Okay. If somebody's project proposal is very bad, I may encourage them to change, but that's not really what the goal you want to put yourself into. Okay. Yeah.
Sorry, is there any grading rubric for things that you look for in the proposal?
Do I have a rubric? No. I think I showed you, I posted some examples of projects that we thought good in the past. Proposals. When I read these things, what do I want to know? First of all, I want to be sure that they are doing something that sounds interesting. Okay. That doesn't sound too trivial. That doesn't sound, sound too boring. Okay. I want to see that they've got some kind of a direction, and that they know what they're going to be doing for the for actually the project. So one thing you could do, a terrible proposal would be to take the text from what I had and copy it down and stick it in there. Okay? Because now I don't know that they've actually, done any kind of experiments, that they've done anything to make sure they really have an understanding of what they're doing. Okay, so that's the main thing that when I read these things, I want to know. Do they have a clear idea of where they're going to go next. And by this, I don't want to see a weekly schedule of what you're going to do. Those I always laugh at when someone says, oh, on this week, I'm going to get the data, and this week we're going to go write 6,000 lines of code, and this week we're going to run some kind of a test. What I really want to see is enough of a understanding of why what they want to do is kind of a cool project, okay? Evidence that they have started to play with it and they know where their data is and they know what kind of things they want to do. That's kind of what I'm looking for. Okay, is that clear enough? Or any other questions about the project proposal? And again, I'm happy to talk with people for projects after this during my office hours. Okay. Any questions? Going once, twice. Okay. What I would like to talk about now, I just like to finish up today. My only real goal for today is I would like to finish up the unit on visualization and talk about some. Again, I think visualization is one of the, a really useful skill to have, okay? To be able to look at what's a good visualization and a bad visualization and have feelings about it. And it's not just in the context of this class. It's just as a skill in, in doing any data project, in any presentation. This is one of these things that I think really pays to know about. So even though it's not hyper technical, I think it is worth thinking about. Okay, so let me go through a few more visualizations that you may not, some of you have seen, some of you may not have seen, and let's form opinions about them. So sometimes you're interested in, let's say you will have a world where you have an x-axis, which is basically time, okay? And the y-axis is some variable. Often people just kind of plot the mean. What is the mean value or the median value of that variable at that time? A box and whisker plot gives you sort of more information than just that, okay? A box and whisker plot has the property that there is a central red line, okay, that is going through this thing that is showing typically the median value, okay? There is a box that is showing you the, the value that would be in the, top quartile, maybe the top 25% and the bottom 70, the 25th percentile and the 75th percentile. And then there are whiskers that they add to the box, okay? These like hairs, okay? That will go up to show the extreme values, okay? The highest and lowest point, okay? How many people have seen these box and whisker plots before? Okay. Do people like them? Okay. Scientists, for some reason, seem to like these. I don't personally like them so much, actually. They look a little like chart junk to me. How would you show this data? Are there other ways to show this data? Do you kind of get the idea of what this is trying to show? Are there other ways that we might be able to show the data in a box and whisker plot that would reveal what was going on?
I've heard of violin plots.
Violin plots. I personally dislike violin plots even more. But what is a violin plot? I may be wrong. I think I know what you mean. That again, you want to show the frequency distribution for what the value is at each time. So if this is the Y value, okay, they have a width around each bar corresponding to the frequency of the items in that bin. So the places that it was more frequent, the violin would be wider the limiting values would be this. So in a violin plot, you would have a world where you had a bunch of shapes that kind of looked like this. Actually, let me make it like this. Man, I'm not doing a great job. It should narrow typically at the extremes. It should get wider in the middle, and it shows the distribution. Okay? Have people seen these before? Okay. What do I like? How might I like this better personally? And again, this is you have to develop your own visualization aesthetic. Just because I don't like violin plots doesn't necessarily mean they're wrong. Okay? Just like the fact that I don't like box and whisker plots doesn't mean it. What do I like better personally? I like I would probably prefer to see a graph showing me what the mean is. I might like to see contour lines, maybe in different colors, showing the 75th percentile and the 25th percentile. Okay, that might interest me. The other thing I sometimes like to see is, and I think is even better often, showing me the mean or the trend line is a good idea. But I really like it if perhaps you show me the actual dots where the data actually is. If the amount of points is modest, if you lightly display the value of the individual variables, I can actually see the, the actual points. And sometimes that's what I like to see. So if you show with enough transparency and lightness, okay, you can show the actual data values from which you produce the mean. And I can, in my head, figure out what the standard deviation must be, at least get an eyeball sense. If these dots are very, very light and transparent, then I can get a thickness, which will give me, the thickness will be like a heat map, which will give me some of the other data of the, your violin plot. Okay. So this is my preference, but either way, this is a way of showing a distribution as it changes over time. That's kind of what they want from here. Any questions about why there exist these things? Okay, and anybody have any other preferences of taste? Okay, fair enough. Another area where taste comes in is, suppose, let's say you have a breakdown, a distribution, of a finite number of labels that changes over time. One way this is a plot of how many of different types of guns, how many of different types of guns were being sold at a particular time. One thing you could use is a array of bar charts, where this shows the x-axis is the year, the y-axis is the total number of guns sold, okay, and they partition the bar into the by category. What do people think of the array of bar charts? Who likes it? Who doesn't like it?
I don't like all the white space between the bars. I think the bar should be fully like 100% width, if anything.
You're saying the white space isn't doing anything for you?
It makes it hard to see because of the contrast.
Yeah, so an alternative to a white space is what people sometimes call a stacked area chart, okay? Where you're now plotting the, you now basically have the points instead, the points, the Y values, instead of bars, and you connect them by polylines, and you color the regions. So this is a stacked area chart, okay? And to my eye, again, I do find the white between those bars distracting because you had too many bars. What's good about a stacked area plot? What do you see in the stacked area plot?
You can clearly visualize the trends in the area for each of the different types of guns.
You can clearly visualize the area for the total. You can kind of visualize the trends of the area for different things. If we take a look at the blue, what are the trends for the blue, the light blue? Can you see the trends year to year for the light blue? To my eye, that's kind of obscured because the bump that you see here is because of the orange, right? You sort of see the blue going up, but that's not really anything having to do with blue. It was because of the orange. Does everybody kind of see it? Implicitly, the total for the amount of that amount is there, okay? But I find that hard to see. An alternate thing is to to show us the to plot each one of to plot multiple lines on a plot showing the sales for each type of gun for each year. That's what we did here. Which is this better for? Okay, what is the thing that what is the the take-home message I get when I look at this one? I'd say, my God, there were gun peaks here and here. People were going crazy in 1983 and in 2010. They had to get a lot of guns, okay? When I look at the second one, I do see, wait a second, the only kind of gun people weren't, that I see more subtle things. I see the real seasonal peaks where it looks like on pistols. Again, I'm not a gun expert, but I gather those are things people carry for self-defense. Where I gather shotguns are probably what people get for going hunting. Okay? And, you see, anyway, I think I see more, I sometimes like these stacked area plots. If you're interested, though, if you want the gestalt trend, it's easier to follow in the stacked area plot. If you want the, just want the, to see the individual components, you're better off with multiple lines on a chart. Any questions? Here are two stacked bar charts for the people from each class on the Titanic, the survivors. This shows who survived when the thing sank, who didn't. So Kate Winslet would presumably have been over here, okay, in the movie. And Leonardo DiCaprio was presumably, no, Kate Winslet was here and Leonardo DiCaprio was here. What is the different thing you get whether or not you have normalized these or not? Because people see that this is the exact same data in some sense, but you get different messages a little bit. What does the plot on the left say? At least to anybody. What do they think it says to them?
That the most amount of people died in third class.
Yeah, that and the casualties were all in the third class, but the third class had the most people, right?
Yeah.
When you normalize it, you see that, again, the first class was the one that cost money. Basically, the message in the first one was, my God, all those people in the third class died. The message in the second one is, it's good to have money, because kind of at that, the survival rates went up in each class. Okay? So a lot depends on what you want to show. Another visualization that, in fact, this is a visualization you will be presumably watching within the next month or so. Our data maps, okay? And a cartogram, okay? A data map, as far as I'm concerned, is a numerical overlay of data onto some kind of a map where the geographic placement of things kind of reflects something important. This is showing the data for the, the electoral votes when Obama ran against Romney, okay? And in the data map on the left, you see each, you see each state with the number of electoral votes it has, colored by who won it. Okay, blue was for Obama, red was for Romney. Now again, in the United States election, I assume many of you know this, but basically you don't win the votes for the whole country, you win the votes for each state, and you get a certain number of votes for each state you win. That's kind of what the Electoral College is showing you. What is the conclusion when looking at the data map? It makes it very, very easy to see, locate for which state is it that you know, which way did a particular state vote, okay? But because the electoral votes are a function of how many people rather than the size of the state, it's sort of, when you look at a map like this, the winner doesn't completely stare out at you. On the map at the left, do people see more red or do they see more blue?
They seem about even.
You think it looks about even? Okay, actually, the election was a landslide in the electoral column for Obama. Okay, he won 60% of the more than 60% of the electoral votes. Yet, because there's this, the power of the value was distorted, you know, did not correspond to the area. When you look at the election map on election day, the Republicans will tend to win in big empty states, okay? So the map is going to look very, very red, even if Trump doesn't win, okay? Another way to view the electoral map is to distort the regions. So the size of each region corresponds to the, to the, you know, to the variable that you want it to be, okay? So the second map is one where they tried to distort the map, okay, so that the size of a state was proportional to its number of votes. So something like New Jersey, which was, you know, is a physically small state with a lot of people in it, starts to show up much better, okay? Any questions? Which do people like better? The visualization of the cartogram, which is trying to preserve the number of votes, or the full map? Anybody have opinions here?
I mean, the cartogram makes it a lot easier to tell who won, even without the little legend in the bottom right corner.
Yeah, so this one has a lot more blue in it, okay? So if you're trying to show who wins, okay, I think that this is more reflective. If you're trying to show what each state is voting, it's hard to find states here because you don't know where they are. They've kind of shifted around a little bit to try to accommodate that.
How do you even create a cartogram though? Like, how do you determine where all these boxes go?
There are good algorithms for doing this distortion. So the answer is, you're right that this requires using a visualization, you know, some kind of an algorithm has to be used to, you know, try to make the areas roughly comparable to the votes while causing the minimum distortion elsewhere. And this is not an obvious thing to be able to do, but there are a bunch of algorithms for it, and you won't have a hard time finding a package that generates these things. Okay, fair enough. Now, there are a lot of other data maps that are used for visualization that I think, when you can kind of map your data in interesting ways, I think that wonderful things happen. And I think that the greatest visualization in world history is the periodic table, okay? Because everybody took chemistry at some point, had to suffer through chemistry. They saw this, okay? You know that in the periodic table, you have the elements arranged, okay? So that, so, and again, the properties of elements are shared by elements in the same columns, okay, which is why the colorings reflect, like these are the noble gases, and you know, and the properties, the colors of the element reflect certain properties to it. You know, does everybody see that there was some decisions? Is the periodic table, the way we look at it, is it a human visualization, or is it just the way the data is? Okay. Is this something that God created because God created chemistry? Or is it that humans created this visualization, and that's the reason why it's so powerful? I will assert that the property, that the periodic table, the reason we like it so much, reflects at least one human decision for visualization. That if they'd gotten it wrong, the periodic table would not be very nice. Does anybody see what that is? Where there was a human decision?
Moving the lanthanide and the actinide series down to the bottom.
Bingo, these guys, okay? If you look at it, these guys over here are all elements that stuck in here. You could have drawn the periodic table by having this be slices, okay, representing each element. Or you could have made this thing incredibly wide and made scandium and ytterbium, okay, to be Yolong, okay? There was a decision to kind of factor these guys out of the table, okay? And that was, you know, that's part of why people can visualize and understand the table very well, okay? Any questions about that? I think looking at classic visualizations is you know, kind of a good thing for inspiration. We should be kind of impressed by the periodic table. Any questions or comments or anything like that? And again, what I will tell you is some of these fancy plots, like the cartograms, okay, you probably could not come up with the algorithm to try to distort the areas yourself, but there are libraries for doing these things in matplotlib, in Python, or in the statistical package R. Okay, R actually has even more extensive visualizations than Python does. Okay, and over the years, I have found that the plots from Excel, which I am perfectly happy that people use Excel to do numerical manipulation on small tables, I find that their plots are not very good. Okay, and that using these other ones, you know, you can do much better. One idea that I really like in visualization are arrays of small plots. Okay, I guess it's not the most interesting data set, but that often, if you have a plot that what you can see is readily visible, having an array of you know, a moderate number of them, you can often see a lot of different things. So here we have an array of 8 plots. Okay, I gather these are data on a bunch, like 20 different software packages. And I guess they were talking about how much their people use each one of these things, use the product for these things. And you can see that, you know, there's certain things that become clear. It becomes clear that, for example, complex ad hoc analysis and predictive analysis is less important than parameterized reports or statistical management reports. You see interesting things like, why is it that these products, it must be that they only do static management reports, and that's why people like using them for that. You know, you want to present your data so the eye has something to look at to make patterns. Any questions? Okay. What else is interesting? It's important when you're doing visualization to take use of color, and often people use color to define scales from so that you can reflect data values going from small to large. Now, apparently, when people define colors, they usually define them on kind of a 3-level scale of kind of brightness, saturation, and hue. Hue, as I understand it, is kind of the distinct underlying, raw color. The brightness of a color reflects kind of how much it's mixed in with black as opposed to white. Okay? And, you can get, things that are from very bright colors to very dark. There's a separate issue of saturation, which is about if you add a neutral color and you mix it in like gray, okay? What is the percentage of In this case, it's a question of you mixed it with bright or dark. Here it's a question of whether it's all the real hue or a fraction of gray, okay? The important, I guess, observation from this is that if you want to show a ordered sequence, okay, people are good at telling the difference. The eye is good at telling the difference between bright and dark. The eye is good at being able to tell the difference between saturated and dull. It's not as good at remembering an order between different hues. So when you set up a color scale, okay, it's often much better to base the color scales on saturation or brightness than it is to base it on like a rainbow scale of hue, okay? What do you see, or what do I see in a rainbow scale? Okay?
Something cyclic.
What? I don't see anything cyclic, okay?
Because like hue wraps around on itself.
You say hue wraps around on itself. Well, I don't.
I mean, not on that diagram for some reason, but like hue does wrap around on itself.
Okay, so you think hue is cyclic, okay? When I see hue, things that kind of bother me when I see a rainbow scale, one is I see typically a big chunk of green and a narrow chunk of yellow. The rainbow scales are not, particularly linear. The gradients of equal size don't register very well. And it's hard for me to remember. If you had to say which is hotter, is it light blue or light green? I typically, I have a hard time remembering that. The kind of color scales that I typically like, one color scale I really like, is when you have, blue, let's say something like this. Hold on. Okay, hold on. Getting lighter to the center, and red, hot out here and getting lighter in here. I can kind of, if it's centered around 0, I can now tell, is it greater than the mean or is it less than the mean? And because if this is scaled by brightness or saturation, I can usually read that better, okay? So think what, when you set up a color map, it's important to think whether it shows what you want it to show. Any questions? And how you use color, okay, is in my mind often makes the difference between whether a chart is easily understandable or not easily understandable. This figure came from a student's thesis exam. One of them was what the student presented, and one of it was I demanded that they change the color scheme, okay, so it was clearer. Which one of these is better? Anybody see what the difference is here? One of them, in my mind, is wildly better than the other.
Right.
Is the left one preferred because it allows you to use the contrast as a key rather than on the right where the
You
really
like
dark
the
colors
left
are-
one because you're saying there's a contrast that I guess the yellow looks different against the green and the yellow, and you're having trouble with the green and the blue? Is there anybody who has other opinions?
I like
The
right.
right one.
Why do you like the right one better?
It's not pinching the eye because the yellow in between, like it's just a little smoother in looking.
Okay, you think it looks smoother, okay?
I
You
think
guys
it's
are talking here about what you call, you're starting to sound like art critics, which I guess is what I wanted in here.
Also, I guess
Also, the
I should have
colors
said
are more
that.
representative.
Yeah, night is yellow. Why is night yellow? I guess.
Bingo, this is what this is what wildly disturbed me about the plot. Night logically is dark. Day is logically light. This is showing you genes that are turned on in the day and turned on in the night, right? By coloring, by making black be night and light be day, okay? The meaning of what this is a lot easier to keep in your head. Does everybody kind of get that idea? Okay. So this is the one that I liked wildly better. Okay. We can argue whether he should have had day before night because it's alphabetically ordered, and I usually like that better. Okay. So I would have probably had day before night. Okay. But there's no question that night is a dark color and day is a, so this is why when, people, I think when you can have colors reflect the properties people internalize, people understand it better. Any questions? Okay. Again, it's good to start looking at these things and looking at masterpiece paintings and develop our aesthetic of what is a good visualization, what is a bad visualization. We talked about this with respect to Tufte. Tufte has a lot of great visualizations that he publishes in his book that he thinks are the world's greatest visualizations, and some that are the worst. But I think it's always good to look at these and develop a taste for what is greatness. Okay. This is his favorite visualization from history. This was from a book published in like the 1850s. And this shows you the fate of Napoleon's army when he went from France to invade Moscow. What is the story of this thing? It is the story of a huge army leaving France, marching across Europe, and it's getting colder, and his army is getting hungrier, and his soldiers are starving. Does everybody see that the thickness of the bar is reflecting how many soldiers he has at that point? He finally gets to Moscow where there is no food. They have burned the place down to make sure his army starves. And it's in the middle of winter. And now he's got to go and retreat back to France. People dying like flies. This is what got back to Paris. Okay? Does everybody see how this plot kind of shows both the size of the army and the the geographic placement? He also shows you helpfully how cold it is at each place. Okay, this is one that he really liked. Okay, any questions or comments about that? This is one that I love. Every year, come around January 5th or so, I get my New York Times and I look at this. This is my favorite chart of the year. What is it? It is the New York City weather chart of the year. What is this showing me? It is showing me, as a function of the day of the year, what is the temperature? What was the temperature? What was the high and low every day? Okay? And it compares it against the average high and low. You see this, this over here, again, if you look, there's kind of a more regular strip that is oscillating. And there is a lighter bounce of the high and low temperature that the city has ever had. What does this show you? This shows you the year's weather playing out against the average high, against the average and record highs and lows. And what do? I find I love to look at this. What is exciting to see? Can anybody see a place where the temperature really changed dramatically? from one day to another. Okay. Where do you see something like that? This must have been pretty exciting to live through, right? Where kind of it went through from a day where the high was below the usual high, shot up immediately. It was unusually cold and then went unusually high within a day. Where is there a record high? Bingo, there was a record high. There was an almost record high, okay? How long does it stay hot when it's hot? Okay, that's what this is kind of showing me. Here was a relatively long period where it was warmer than usual, okay? This has like 3,000 numbers in it, and yet you can understand it and see what's going on. This shows the amount of rain. June was a rainy month. That was bad. Okay, that's probably why it got so cold, was because it got so much rain then. Okay, any questions? I like that visualization. This is one of Tufte's favorite visualizations, which is very, very clever. This is a train schedule. You guys hopefully will eventually take the Long Island Railroad back and forth between Stony Brook and the city. This is a similar train schedule. This is between Paris and Lyon in France, okay? What is it showing you? The x-axis is time. The y-axis is the position of the train. Have you ever seen a train schedule like that? I hadn't seen one. What's interesting about it? Each line represents each one of the diagonal lines represents a train. What can you see on this train schedule? Okay, to know that you can't easily tell from a normal train schedule. Can anybody see anything?
It shows the route as well as the duration plus
It
the
shows
stop.
the route. Well, the route, I guess, is this, okay?
I mean, like, I can't read the last station, but if I'm going from there, it waits for 1 minute, if that's minute, and then it goes to, can't read the names, but like somewhere.
Okay, so it shows you, okay, so these are the stations. First of all, let's read a couple of different things. What does it look like? How can you tell the trains from Paris to Lyon? Which one are they? Which ones are the trains from Paris to Lyon? Can anybody tell? What represents the trains from Paris to Lyon? Okay, they are all the trains that are diagonal, where the position on this line is increasing with time, right?
Yeah.
If you have a diagonal line like this, okay, the train that's going down that way is one that, is going from Paris to Lyon. Other ones that are going in the other, which are going up, are the trains from Lyon to Paris. Does everybody see that?
Yes.
What things can you tell from this that you can't tell from a normal train schedule, which you guys have probably seen? Which is the fastest train? How would you tell whether a train is fast?
The first diagonal? No. Oh no. The different, the steeper one.
The slope, a steeper train is a faster train, right?
Yeah.
There's a question I have about this diagram though. How do you know if a train stops at a station versus just blowing past it?
Okay, so at this point, my guess is that they stop at every station. But if they wanted, how would they show it if they wanted to show it? They probably could put a dot at a place where there was a stop, right? If you wanted to show that, let's say it was an express train, maybe, or let's say it only stopped at a few stations, you could probably have put a dot wherever the train actually stopped.
Like the visualization seems cool, but it seems like something that I would never want to use when traveling because it's not reliable when I try to figure out how to navigate. Because like I don't know which station to stop which train.
I would,
Well, okay. One would claim it may probably stops at every train at every station, but if not, we could lay that information on there if you don't like that. Okay. But there's other things you could tell from this thing. Where can you get on? Where should you be able to? Where are you going to? Should you go to have lunch?
maybe a little more of colors could indicate like which.
More of colors. Well, this was made in the 19th century. I'm not gonna complain to him about colors.
No, I mean,
Okay.
about what
But I
could,
do find interesting. Again, what does a flat line mean? A horizontal line. What does that mean?
It
Stopped at the station. You should get off and have lunch. That's what it tells me. When should you pull your arm in from the window? If you have your arm sticking out the window, when should you pull it in?
Sticking your arm out the window?
What?
Sticking your arm out the window?
It's hot. It's hot in the train. They didn't have air conditioning. You open up your window, you stick your arm out. When's it a bad idea to stick the arm out the window?
when the speed is really high, and that would be like when it is.
And when the speed's really high, I say, when you've got an intersection point between a train coming one way and a train going the other way, okay? That seems to me to be a bad thing, okay? So this is something, when are you going to look out the window and see a train? That's going to be it. There's a lot of information here that is shown, okay? And I find this a very imaginative visualization. This is one of the most famous visualizations from history, actually. And that's gotten a lot more play. I've seen this in the newspaper in recent months. This is a data map that was produced by a public health official trying to figure out what was the cause of a London outbreak of cholera, which was a disease, okay? And what is this showing? This is a data map showing where there's a dot for wherever there was a case of cholera. And there is an X wherever there was a water pump that people would go to bring their pail to get water from. Okay? What does this kind of make clear? Here is an X. Okay? Here are the other X's. What does this kind of make clear? This is pretty convincing that the reason why there is this density of all the cholera cases is because it's around this water pump. And all that they did was to end the cholera epidemic was they apparently took the handle off the pump. And once they did that, then people went elsewhere. And then the outbreak ended, okay? And so this was a classic example of that, of a data map. This is one visualization that he had that I always find kind of compelling as an example of a difference between a good and bad visualization. This is over here is a historical visualization. I don't know, when you guys were probably very young, the United States had this ship called the Space Shuttle that would try to fly into space. And when I was in grad school, the Space Shuttle blew up, okay? They launched the rocket, and the ship exploded right after taking off. Okay, and before the launch, it was very cold that day, and the engineers desperately tried to convince management that it was too cold to launch the rocket, that there was going to be something bad that happened with the O-rings. And they made this graphic. They said, look, this shows us all the damage to O-rings, okay, on the left and right rocket, okay, for each of the 24 launches we've had so far. And I show you where the damage is. And I show you what the temperature at the launch time is. There's no way you should launch that rocket. What did management look at when they saw this? Do you see that in this plot? That it's disastrous to launch the rocket? Well, management said, you guys are eggheads. You don't, can't give a good presentation. We're going to launch the rocket. The right was an example of a graphic where Edward Tufte redrew, okay, the data that was given here. The x-axis, the x-axis was the temperature at the time of launch. The y-axis was a measure of how much damage the rings had gotten on each launch, okay? And he had an index of counting how much damage there was, okay? And what he was able could show, if you look at this, is, well, this shows that these are all the launches here where there was no damage and it was pretty hot. And there were a couple of launches where we had a little bit of damage. But if you notice, actually, we had a few rockets launches where it got kind of cold, okay? And if you look at the one with the biggest, amount of damage, was on the coldest day, okay, that we've ever launched. And tomorrow's weather is here. See the fit between damage and temperature? What could happen tomorrow? The damage is going to be over here, okay? If you make this graphic, it's obvious to management you don't launch. If you did this, okay, the message didn't come out. Does everybody see that this report visualization makes very clear what was going to happen? This one, you know, presented too much information with chart junk in a way that people couldn't understand it. Any questions? People kind of agree with that? Okay. One other visualization that I added because I liked it today was that I find very compelling is with our presidential election. If I go to my favorite website, 538, this shows me, you know, the current state of the presidential election. I'm concerned who's going to win, okay? And what does this chart show? This chart shows every state in the union, okay, based according to the polls, how likely it's going to vote Republican and how likely it's going to vote Democrat. And it's sort of ordered by from most red, most Republican to most Democrat. And so the color reflects how sure is it, which way is it going to go. And they have a line separating where, they have the states ordered by how likely they're going to go. And they have a cutoff at where is the margin of victory. So what does this chart tell me today? It tells me that if Biden wins Pennsylvania and all these other states, okay, that he will win the presidency. It tells me if he didn't win Pennsylvania, there still are some other states like Florida and Arizona and Arizona and North Carolina, Ohio that currently are leaning towards him. Okay, so he has some other ways to win. What about Trump? Well, Trump's got to find a way to reverse this state and reverse this state and reverse this state and reverse this state and that little district and Pennsylvania. Okay. So this to me shows a lot of information. You get to see the states from most Republican to least Republican. You see what scenarios have to happen in order to do what the critical states are. This to me is a very informative visualization. Any questions? Why is it good that they wrapped it around like a snake instead of just doing it in order?
It would have been
just having a
stupid.
long line with this information.
You couldn't fit it on your monitor.
What?
You couldn't fit it on your monitor if you did that.
You couldn't fit it all in your monitor unless you shrunk it to very, very small, right? You could have one of these linearly, but you get a lot more area snaking around like that. Okay? So to me, this is a very good visualization, and I really like that. Any questions? Okay, just because I don't like that one so much. Let me just show you a couple of terrible student visualizations by comparison so you learn not to do these kind of things. Here is a frequency plot somebody showed me. Okay, what's wrong with this frequency plot? This shows me for the items ranked from 1 to 120,000. What was the number of times that they got sold? What's wrong with this plot? It obviously isn't very exciting to look at. What would be a way to make it better?
Remove that outlier so the scale works better.
One possibility is remove the outlier. And you know what would happen in this case if you remove the outlier? You know what it would look like? Actually, it would look exactly the same. Okay,
Logarithm.
see over here, there's another potential next outlier there. Okay, trying to remove the outlier is one possibility. Anything else that you could do to make this better?
A logarithmic y scale.
Log.
Put it on a log scale. Suddenly, when you put it on a log scale, suddenly you see things. This was a log scale. And you say, gee, there are a small number of things that are pretty large. You put it on a log scale. Now you see a straight line. You say that's a power law. Okay? So that was a very misleading, that was by adjusting the scales right, that can be the difference between showing something or not showing something. Here is a plot that my students produced, a student produced once for me, where the x-axis is basically the length of the gene. Again, genes, genes are of different length. There's short genes and there's long genes. And we were measuring something called the average energy per, we wanted to know the average RNA structure, which was measured by a quantity called energy of each gene. What does this plot tell you, looking at it? What do you see with this plot? What is this plot trying to say? Any ideas? What are the features that this plot has? What do you see when you look at this plot? Is there an impression of something?
Till a certain distance, the mean energy is not fluctuating that much, and then it dips. Like there are a lot of dips.
She's saying, my God, it looks like as you get longer, the mean energy goes down. That's what you're saying.
It also goes up at times, like if
it goes up. Okay, something strange is going on, right? Well, what was the story? If you look at how many genes there are of a particular length, there are a lot more short and modest genes than there are. This is a cumulative distribution. There are a lot more short and modest length genes. Very, very long genes are rare. So what does that say about the average?
oh,
Here you're averaging a small number of things. Does everybody kind of get that? Okay. If this is a small number of things in each bucket, the average is going to be very unstable, right? Really, what this is showing us is that by the time you get to 1,000 or something like that, you've seen almost, everything here is going to be very, very thin data. And so the real thing that you want to see is probably the plot only cropped up to here. And then when you look at it, you see that there is very little impact of that the average energy is the same, regardless of gene length, which is really what the take-home message is. Any questions? Sometimes when you display the full range of your data, okay, if most of the range is the stuff where there's not most of the data, okay, you get weird perceptual effects. and cropping it can be the healthier thing to show what's really going on. Any questions? Okay, I encourage you to look at, this is all I want to really say about visualization.